Today, we're going to talk about Canopy and our experience building an open source real-time monitoring framework designed specifically for CDNs. Here's a roadmap for our presentation. First, we'll give some background on CDNs and monitoring. Next, we'll talk about the CDN monitoring space and the solutions that existed before we built Canopy. Then, we'll discuss what it took to build our prototype. Finally, we'll wrap up by going over what we did to improve our prototype and arrive at our final architecture. Before we discuss how Canopy works, we need to review some basic concepts like CDNs, monitoring, and what can be gained from monitoring the CDN. Let's first take a look at content delivery networks. A content delivery network, or CDN, is a geographically distributed network of servers that stores cached versions of web content like HTML pages, images, and videos at locations close to end users. Using CDNs can result in two major benefits for web applications. First, CDNs reduce latency. Two users requesting data from the same server may experience different response times depending on how far they are from that server. CDNs help to reduce that distance. Take these users, for example. Instead of every request they make being served by the European origin server, a majority of their requests are served by the edge location closest to them, reducing the distance the data travels and providing a faster experience for the user. The second major benefit that comes from using CDNs is they can lower the load on a company's web servers, otherwise known as origin servers. A request fulfilled by the CDN is a request the origin server didn't have to address. Now, CDNs are widely used, and companies are dependent on them to provide these benefits as well as a few others. How can someone make sure that their CDN servers are in tip-top shape, serving resources as efficiently as possible? This is where monitoring comes in. Google describes monitoring as collecting, processing, aggregating, and displaying real-time quantitative data about a system. By visualizing aggregated data, it's much easier for developers and system administrators to recognize trends and gain insight into the health of a system. But in order to monitor a system, we're going to need some data, specifically telemetry data. Telemetry data is data that production systems emit to provide feedback about what's happening inside the system. The three main telemetry data types used in software engineering are logs, metrics, and traces. We are concerned primarily with logs and metrics. So what can logs tell us? Logs are timestamped records of events that occur within a software system. This image shows a CDN log. It has information about the date the event occurred. It shows us an IP address. It even tells us which HTTP method was used during this event. This is where logs shine. Logs provide a ton of data about one single event. When we want more information about our system as a whole and how it's changing over time, we turn to metrics. Metrics are a numerical representation of data. They're usually smaller in size than logs, have fewer fields, and measure a single aspect of the system being monitored. Metric data can be presented in a dashboard, offering a comprehensive view of a system's overall health. But what exactly goes on that dashboard? Which metrics should we follow to get the best view into the health of our system? Google answered these questions when they identified the four golden signals of monitoring: latency, errors, traffic, and saturation. Taken together, these four signals serve as a guidepost for monitoring teams and provide developers with a well-rounded understanding of what is happening in production systems. CDN log data can provide us with insights into each of these four signals. So why go through the trouble of gathering these logs and metrics and keeping tabs on the four golden signals in the first place? Well, although CDNs currently handle an estimated 72% of all internet traffic, they are in many ways a black box. The physical infrastructure that makes up the CDN is operated by third parties and is largely outside of our control. Therefore, Monitoring the logs generated from CDN traffic is one of the only ways to gain observability into this system. Let's see what it takes to crack open that black box and effectively monitor the CDN. The first thing we'll need is a data pipeline. Data pipelines are systems that process and move data from a source to a destination. A logging pipeline is a kind of data pipeline for log-based telemetry data. Telemetry pipelines have three key stages: emitting, shipping, and presentation. Let's look at each stage. First is the emitting stage. In the emitting stage, data is accepted from production systems and prepared for shipment in the logging pipeline. Next is the shipping stage. The shipping stage takes raw log data from the data source and moves it to storage. In order to do this, there are three necessary steps: collection, transformation, and storage. In the collection step, emitted data is gathered, batched, and prepared to be read. Next is the transformation step. During transformation, data is decoded and parsed to extract relevant information. Last comes the storage step, where transformed log data is aggregated and exported to a data store where it can be later accessed and queried. The final stage in a logging pipeline is presentation. This is where log data is queried and visualized through a user interface. Here, users make sense of the data and derive insights for various purposes. Now, I'll pass it off to Michael, who will talk about the challenges involved in building a logging pipeline.
Thanks, Alex. Now that we have a better understanding of what a logging pipeline is, let's take a look at the challenges associated with building one for CDN data. Building a pipeline for CDN log data has a unique core challenge. CDNs emit massive amounts of log data. So how much data does the CDN emit exactly? Let's take a look. When a user opens a web page, their browser might issue many requests to the CDN. Why is this? A single web page can consist of a variety of different assets, such as images, JavaScript, HTML, and CSS files. Their browser will issue requests to the CDN for all of these resources. Each of these requests will then hit the CDN layer. This means that traffic from a relatively small number of viewers can add up to a large number of requests at the CDN. Because of this, traffic to small or medium-sized web applications can end up generating millions or even billions of CDN logs. This presents a challenge to engineering teams at these companies who need to handle all this data. An example is Love Holidays, an online travel agency based in the UK. Love Holidays states online that they handle more than 30 gigabytes per day of CDN logs. That is quite a lot for a medium-sized company to deal with for just one type of telemetry data. The large flow of data has important implications for our project. Specifically, it affects data ingestion, the way we query and visualize data, and the storage requirements for our pipeline. Ingesting CDN log data into a pipeline can be challenging. Internet traffic tends to be bursty, similar to traffic at a major train station, which might be busy during rush hour, but nearly empty in the late evening. The pipeline needs to be able to handle this varying flow without slowing down or backing up. An equally important challenge is how to efficiently query and visualize CDN log data. Monitoring the CDN requires running analytic queries, like data aggregates, where we perform mathematical operations such as sum, count, min-max, and average over a large portion of the dataset. This can be slow and expensive to run, especially with such large datasets, and we need to do all this in real time. This poses a significant challenge. Aside from efficiently running analytic queries, a storage solution for CDN logs has three major requirements. First, it should ideally be able to store and retrieve every log line the CDN emits for debugging and compliance. This means we cannot sample the data or only store a small portion of it. Second, it needs to support efficient compression to reduce the size of the dataset. Third, it should support fast insertions for the batch log data. To review, even a small number of users can generate many requests to the CDN, resulting in huge log datasets. These datasets are difficult to work with and pose various challenges to a logging pipeline. However, these technical challenges are not the only considerations teams need to keep in mind when choosing a monitoring solution. Different solutions offer different trade-offs that we need to consider. So what options are available exactly? Let's take a look at existing solutions available to teams that want to monitor the AWS CloudFront CDN and their various trade-offs. These teams have a few options. First, they could use the CDN's native solution. For CloudFront, this would be the included reports and analytics page. These solutions are easy to use and don't require teams to send data to a third party, but don't easily integrate with other observability data, and in Amazon's case, don't offer customizable dashboards. They could also choose a SaaS solution or software as a service, like Datadog or New Relic. SaaS solutions have several advantages. They are easy to use, integrate with other observability data, and feature customizable dashboards. However, SaaS solutions are not ideal for teams that have strict data ownership requirements because it requires them to trust a third party with their data. They can also be expensive. Finally, they can choose to build a DIY solution. DIY solutions give teams full control over their data and can have robust features. However, they require substantial developer time and are not easy to use, as teams would need to build and maintain their own pipeline. For some teams, both SaaS solutions and the AWS native solution may not work for their specific use case. However, they may also not want to devote substantial developer time to building a DIY solution. This is where Canopy fits in. Canopy incorporates the ease of use of a third-party SaaS solution with the data ownership and control associated with a DIY approach. Canopy's architecture is built using open source components that are configured within the team's own AWS account, allowing them full control of their data. Canopy also features customizable real-time dashboards and fully automated deployment. Let's explore how to use Canopy for your team's monitoring needs. Canopy is designed to be easy to use and require minimal configuration. The pipeline can be deployed to AWS from the CLI in one command using Canopy deploy. Canopy's Grafana dashboards are used to monitor CDN data in real time and offer visualizations corresponding to the 4 golden signals. This image shows the CDN logs overview dashboard, which is your main landing page for monitoring your CloudFront distributions. The top row shows the overall cache hit ratio, as well as information related to errors and total requests. There are 2 other Grafana dashboards titled Client Information and Performance, which offer different visualizations focusing on client data and performance-related metrics. Canopy also has an admin dashboard displayed here. From the admin dashboard, users can conveniently deploy and configure pipeline infrastructure, as well as monitor the status of pipeline architecture after it has been deployed. From the admin dashboard, teams can also configure quick alerts with the click of a button. Quick alerts send email notifications to teams when certain thresholds are met corresponding to the golden signals. Now I'll hand it off to Jason, who will walk us through Canopy's core architecture.
Thank you, Michael. When building a logging pipeline, we knew that we needed an emitting stage, a shipping stage, and a presentation stage. And so we set out to build Canopy. We started by mapping out the core components we needed for each stage of its pipeline. During the emitting stage, the CDN emits a continuous flow of logs as users make requests to the CDN. The shipping stage has 3 necessary steps: collection, transformation, and storage. For collection, we needed a stream to collect and store logs in real time as they flow from the CDN. For transformation, we needed a log transformer to transform those logs to a format appropriate for storage. For storage, we recognize a need for both a log shipper to buffer and batch the transformed logs, and the database, where we insert and store the batched log data. During the presentation stage, the visualizer queries the data stored in the database and visualizes the results in charts, graphs, and tables in real time. Now, after pinpointing these core components in a diagram, the next step that we undertook was to build a working prototype based off of this architecture. And it was during the course of prototyping that we encountered a number of challenges. The first and most difficult challenge we faced was data storage. What database do we choose for storing log data? We considered various options: Elasticsearch, a time series database such as Timescale, and a columnar database such as ClickHouse. As Michael outlined earlier, our use case has unique requirements due to the nature of CDN log data. We wanted to be able to efficiently handle data aggregates, and we also did not want to sample the dataset. Therefore, we need to consider a couple of things: the level of indexing in order to minimize storage needs and preventing sampling. And we also need to consider the type of queries that each database optimizes for. Ultimately, we decided on a columnar database, more specifically ClickHouse, because it offered sparse indexing and it had a column-oriented approach to processing data, thus optimizing for aggregating multiple metrics over time. Now that we had chosen ClickHouse as our database, the next challenge was, how do we move log data from the CDN to ClickHouse in real time? This represents the shipping stage, and so we needed stream storage, a log transformer, and a log shipper. By default, CloudFront real-time logs are delivered from the CDN to AWS Kinesis data streams, a fully managed service for collecting and storing data in a stream. After the logs are stored in the stream, we needed a way to deliver them to our log transformer. One option was to build an application that would read data from Kinesis data streams, process the data, and deliver it to the next destination. However, we decided to prioritize development speed and reliability. We chose AWS Kinesis Firehose, a fully managed service for data delivery. It has a minimum buffer interval of 60 seconds, and therefore provided us with a near real-time solution for delivering logs. And any logs that fail are sent to S3, which is AWS's cloud object storage offering. Finally, we needed a log transformer and log shipper. One option was to build these components. Building a log transformer and a log shipper in tandem would streamline our overall architecture. Ultimately, we opted to use Vector, an open source tool for aggregating, transforming, and routing observability data. Since Vector was out-of-the-box compatible with both Firehose and ClickHouse, it was a convenient choice to use as a data pipe between both of those components. It could also do log transformation, and so Vector could fulfill the dual function of both log transformer and log shipper. The next challenge we faced was figuring out the nitty-gritty of data transformation. How to transform CloudFront logs before loading the data into the database. On the left, we can see that each CloudFront log is emitted in the form of a plain text string, and it doesn't include any predefined fields. With Vector, our log transformer, we can use its built-in parsing function to write a custom regex pattern. This pattern converts the log to a structured JSON object, maps field names to their corresponding values in the log, and converts values to the appropriate data type, whether it be Unix timestamp, integer, or float. At this juncture, we had tackled a number of challenges: data storage, moving data in real time, and data transformation. After successfully doing so, we had developed a working prototype on our local computer. But there was one final challenge we wanted to address, making it so that anyone could set up and start using Canopy and do so as easily as possible. And what that meant was deploying Canopy to the cloud. With data streams and Firehose, we can create these resources directly with AWS. For the other components, which comprise the Canopy backend, Vector, ClickHouse, and our visualizer Grafana, we needed to figure out their deployment. As our first objective, we wanted to successfully be able to deploy the Canopy backend locally. For our local deployment, we chose to use Docker as our solution. We use Docker to containerize our backend components and deploy them as containers on a host. Because data persistence and service discovery is built in, our containers would automatically communicate with each other over a private network, and the data in our database and dashboards in Grafana would persist and they would never be lost. Docker also integrates well with AWS. And so once we got this setup working locally, moving the backend to the cloud would be doable and simplified. After successfully deploying the Canopy backend locally, the next step was deploying to the cloud. And we considered two options: Amazon EC2, a virtual private server service. In this case, we ran a virtual private server, otherwise known as an instance of EC2, and run our backend as Docker containers within the instance. The other option was Amazon Elastic Container Service with Fargate. ECS and Fargate are fully managed services and would remove the need for manually managing and scaling our containers and infrastructure that they're hosted on. Ultimately, for simplicity purposes, we opted for the EC2 instance. Deploying Docker containers on EC2 mimics deploying on a local computer. Configuring our containers to work with ECS and Fargate for data persistence, service discovery, as well as network security had substantial complexity, and we decided to forego that complexity for creating a working prototype. Here we present our prototype's architecture. Starting from the top left and moving to the bottom right, Canopy automatically deploys for our users Kinesis data streams, Kinesis Firehose, Vector, ClickHouse, and Grafana, all on AWS infrastructure. And with this prototype, we had a working solution, and its core components are compatible and play well with each other. However, during the course of our prototyping, we came across areas where we felt we could improve upon how Canopy could better suit its use case. And so now I'll be passing it off to Mehdi, where he will be discussing how we set out to optimize and refine our current working version of Canopy.
Thank you, Jason. Before we discuss the steps we took to improve the core pipeline, let's review Canopy's core objectives. When we set out to build Canopy, two of our key goals were ease of use and real-time dashboard updates. We wanted to create a solution that would be as easy to set up and use as possible. We also wanted to deliver a true real-time experience, meaning our dashboards would update instantaneously as log data streamed in. After building our prototype, we identified limitations in our architecture to both of these goals. Our initial prototype relied on AWS Firehose to deliver data from Kinesis data streams to the log transformer, Vector, over an encrypted HTTPS connection. This approach exposed several limitations. First, Firehose HTTPS requirement limited ease of use by making configuration more complex. Specifically, it forced our users to create a new domain or a subdomain, generate their own TLS certificate file, upload the certificate, maintain certificate validity, and update the DNS records with the IP address of our dynamically generated EC2 instance. This placed a real burden on the user and made our solution more difficult to set up and use. Furthermore, Firehose buffers data for at least 60 seconds before streaming it to its destination, resulting in unwanted latency. Latency is also introduced by the HTTPS connection between Firehose and Victor. A three-way handshake plus a TLS handshake means 3 additional round trips across the wire before log data transfers to Victor. This is in addition to a 3-way handshake from Victor to ClickHouse. This introduced over a minute of delay before logs could be stored in the database and visualized in Grafana. This delay prevented Canopy from being a true real-time experience. To address these limitations, we decided to build a custom log transformer and shipper using AWS Lambda. This approach allowed us to simplify the architecture, eliminating the need for both Victor and Firehose. The Lambda function fulfills 2 critical roles. First, Lambda acts as a log transformer, replacing Victor. Second, Lambda acts as a log shipper, replacing Firehose. In addition to simplifying Canopy's architecture, our Lambda-based solution offered the following benefits. First, using Lambda gave us complete control over log buffering. We could adjust the buffer to imitate Firehose 60-second buffer or achieve a more real-time buffer as low as 0 seconds, depending on the needs of our users. Second, the Lambda function allowed us to ship logs over HTTP or HTTPS to an external endpoint on AWS service, making configuration much easier, as well as providing flexibility and ease of integration for our Dockerized backend stack. Third, logs could now be parsed and routed directly to the ClickHouse database from the Lambda function, removing the additional latency and network hops described earlier. Fourth, when our Lambda code throws an error, Lambda records a log that details exactly what happened, which is convenient for debugging network and infrastructure faults. Firehose does not provide these logs, making debugging frustrating. Fifth, the Lambda function's ability to process up to 10,000 records per invocation aligned well with Canopy's need to handle a massive number of logs, surpassing Firehose's maximum batch size of 500 records. While building a custom transformer shipper brought several advantages, it also introduced new challenges. Particularly, we needed to account for ephemeral network failures, display consistent metrics, and archive failed logs for debugging and compliance. In our prototype, Firehose handled failed logs for us. It routed any batches of logs that failed to be delivered to the database to an S3 bucket for storage. Because we had replaced Firehose with Lambda, we needed to implement similar functionality ourselves. This means we needed a way to route failed logs to S3. However, this presented a problem. Failed logs stored in S3 cannot be visualized in our Grafana dashboards, which would result in inaccurate data and metrics for our users, specifically in the event of ephemeral network outages. To address this issue, we used Kinesis data streams as a buffer for failed logs. When a batch of logs cannot be inserted into ClickHouse, our Lambda function throws an error. Rather than ship these failed logs immediately to S3, the log data is put back into the stream where it can then be retried. Only after the data reaches a maximum retry limit would it then be sent to S3. This ensures that ephemeral network outages would not result in inconsistent data in our Grafana dashboards. However, not all errors are ephemeral, so we still needed a way to move failed logs to S3 for persistent storage after a certain number of retries. To address this issue, we created a separate pipeline for handling failed log data, composed of a dead letter queue managed by AWS Simple Queue Service and a Lambda function that pushes failed logs to S3 for persistent storage. Kinesis data streams pushes failed logs to the queue when the batch has failed after multiple retries. The Lambda function then reads from the dead letter queue and stores the failed logs in S3 before clearing them from the queue asynchronously. While this approach introduced added complexity, it ensured that failed logs would be archived for debugging and compliance needs, supporting our core use case. This improved architecture offered our users a truer real-time monitoring experience and also simplified deployment while still accounting for network failures. With the core pipeline elements in place, we turned our attention to quality of life improvements. This included adding support for monitoring multiple CloudFront distributions in parallel, as well as creating an admin dashboard for pipeline management. Let's first discuss multiple CloudFront distributions. It is not uncommon for developers to have multiple CloudFront distributions in a single AWS account, as distributions can have different settings for different domains and web applications. To cater to these users, we introduced native support for handling multiple parallel distributions within Canopy. When considering how to implement support for multiple CloudFront distributions, we evaluated two main options: parallelization and consolidation. The first option was parallelization. This meant parallelizing or duplicating pipeline components for each CloudFront distribution. In the image, we see each CloudFront distribution delivers logs to its own data stream and Lambda function. Parallelizing components could help our pipeline scale by adding extra capacity. However, we opted to parallelize as few components as possible and instead consolidate log data from different CloudFront distributions into the same pipeline. This is because duplicating infrastructure can escalate costs and complexity. Ingesting logs from multiple distributions into a single pipeline was simpler and more maintainable. The other improvement we made was building a custom admin dashboard. We adopted a 3-tier architecture with a presentation layer, an application tier, and a data tier, where a React UI communicates with an Express backend server and an app server, and SQLite for storage. In addition to the features described earlier in the presentation, the admin dashboard was designed to help monitor the Canopy pipeline infrastructure. It collects and presents metrics from ClickHouse and Grafana instances, enabling users to monitor the health of their deployed pipeline infrastructure. It also displays a list of configured CloudFront distributions, the data of which is stored in an SQLite database. This capability provides users with a seamless way to track and manage their various distributions. With that, we arrive at our final architecture. The diagram outlines the flow of logs through Canopy's login pipeline. First, one or more CloudFront CDN instances emit log data, which is ingested in our pipeline via AWS Kinesis data streams. On the left side of the pipeline, the logs are then parsed and transformed by AWS Lambda and then shipped to ClickHouse. Grafana visualizes the logs stored in ClickHouse and sends email alerts to our users when metrics reach certain thresholds. On the right side of the pipeline, failed logs are processed by the failed logs pipeline and stored in S3. In conclusion, building Canopy proved to be an interesting challenge. It involved complex research as well as careful planning, debugging, and testing. In the end, we achieved our objective of building an easy-to-use, fully automated, real-time login pipeline for CDN log data. However, there's always room for improvement, and we hope to continue our work and improve Canopy in the future. Some of the features we would like to incorporate in future iterations of Canopy include adding the ability for users to perform custom transformations and enrichments on log records, improving the quick alerts feature, making it more customizable and offering more options for notification settings. And we'd also like to add adding configuration options for ClickHouse and the EC2 instance. And with that, we open up our Q&A section.
Thank you, Med. So yeah, as Med just said, we're going to start our Q&A session. Thank you all for attending. So we're going to give everybody a few minutes to write questions. You can write questions in the Q&A comment area. And in order to start off the discussion while we're waiting for your guys' questions, I'm going to ask Med, what do you think was the most challenging aspect of building Canopy?
Thank you, Michael. Personally, it was AWS docs and their inconsistencies. And yeah, there were a lot of inconsistencies we found when we were trying to build when we were trying to automate the deployment pipeline for Canopy. Yeah, I can go into further details, but if somebody's interested, I can go in more details.
That's okay. Thank you, Med. We have our first question. It's from Fred Durham, and he asks, let's start with an easy one. How did you come up with the name Canopy? And actually, I think I can answer this question. So we thought for a pretty long time about the best name for our project. And Canopy is meant to convey a few different things. So Canopy is, as in a rainforest canopy, is the interface between the cloud and the forest below it. And that seems like a fitting idea for a CDN monitoring pipeline, which is sort of the interface between the cloud and your architecture. But also, because it's high up in the trees, you can observe the forest below. And because we are a monitoring pipeline, we also felt that that fit with our use case. So thank you for the question. Oh, and we have another question. So Anthony Alexander asks, what made you choose this project over other project ideas in the context of showing off skills to potential employers? Does anybody want to answer this question? Maybe Jason or Alex, do you want to give it a shot?
Yeah, sure. So in terms of the context of showing off skills to potential employers, we felt like this project actually covered a lot of different interesting areas. On the one hand, we had built an admin dashboard, and that involved web development and creating an application in TypeScript with a React front end, Express backend, and a database. As well, it also involved having to figure out and stitching together a series of tools that will all be sort of compatible with each other, at least in our initial prototype. And as well, with deployments, the first step we took was to deploy with Docker containers. And then we had initially tried the Elastic Container Service with Fargate option first. And there was a substantial amount of complexity. And we felt that at least a better first step would be to do the EC2 instance. And so we felt like it covered a lot of different aspects of development, whether it be deployment or web development, as well as wrapping a framework together with different tools.
So thank you, Jason. We have another question from an anonymous attendee, Mysterious. And the question is, seems like the database was one of the bigger decisions. Can you go into more detail about your database decision? And yeah, I think all of us can talk a little bit about this if we needed to, but yeah, I can definitely answer this one. So choosing a database was a really big decision for our project because we had a very data-focused project. The whole idea of our project was to take this massive stream of log data and then process it efficiently and visualize it efficiently. And we ended up choosing ClickHouse, which, as we mentioned, is a columnar database for a couple of reasons, but one of the most important reasons we considered was its ability to quickly run data aggregate queries. ClickHouse has a columnar database, and because of the way it stores data, tends to run data aggregates more quickly. And actually, there's a couple of real companies in the CDN monitoring. I don't know if it's fair to, it's not the CDN monitoring space, but a couple of real companies that are monitoring the CDN use ClickHouse. So Cloudflare, for example, which is obviously a CDN company itself, uses ClickHouse internally for CDN monitoring. So we were kind of inspired by real companies who had gone that direction. I don't know if anybody wants to add any more info, any more context to that, but thank you for that question. Okay, so we have another question, which is, what was it like working as a team? I think we work really well as a team. Do any of you guys want to comment on that?
Yeah, sure. I'll agree with Alex. I really enjoyed working with Alex, Med, and Michael within the context of a team. We had heard that other teams, there was a high probability of having communication issues or conflict, and for us, actually, it was pretty smooth. And I feel like all of us had a respect for other people's personalities. We tend to be very introverted. And I really liked how each of us sort of respected each other's space to work on their own, but also, yeah, when we did need to work together, either in pairs or, to have discussions, we did. But the fact that we were able to also respect each other's space to either work on our own or we need to explore a particular path. And we just did not get offended at all when we would have our discussions. We were free to sort of express ourselves and say whatever we wanted, and none of us would be offended by each other or be threatened by another person's ideas. And so that's at least for me, that's something I really, really appreciated about everyone on the team.
And Michael,
Yeah.
I believe there's a question before that from Nabil.
Oh, okay. Yeah, do you want to read it, Med?
Sure. So this question from Nabil says, from a SWOT analysis perspective, what would you consider the biggest external threat to Canopy's core service? In other words, what would possibly render Canopy useless? Could you elaborate more on what you mean by what do you mean by the abbreviation SWOT, Nabil?
So while we're waiting for that, we have another question. So thank you guys for all the congratulations and great job, by the way. Really appreciate it. I know we probably have some other Capstone grads and students, so great job to you guys as well. Keep up the hard work. We have a question from Sho Sugihara, who asks, what part of the project was the most fun to work on? Does anybody want to say what was the most fun to them? Maybe Alex, because Alex, you haven't talked since the beginning. You want to give this one a go? What was the most fun to work on?
Sure, I'll chime in here. Yeah, I would say, I mean, it's like corny, but like I think all of it was fun. I think working with people, people on the team, and then our mentor was terrific, and our launch school staff was incredible. So I think the most fun part for me was just collaborating with people and realizing that on a team you can do way more than you can do by yourself.
So Nabil elaborated that it's strengths, weaknesses, opportunities, and threats. Yeah, I think it's an interesting question. What are the things that could bring down our pipeline potentially? It's something that we thought about. And as we went into a little bit when Med was talking earlier, one of the advantages of using Lambda that we talked about was actually that it made debugging easier, because there were times where if log data isn't inserted correctly, if the request isn't formatted correctly, like things can go wrong in the logging pipeline. But one of the things that I think we could work on more in the future is things like load testing, just putting our pipeline under more stress. We tested it. We actually built a testing program. We called it Request Monster, and Request Monster basically just sends like many different requests to hit the CDN, and then like the more requests Request Monster sends, the more logs that generates, and those logs hit our pipeline. And so we did test the pipeline under a certain amount of load, but I think there's probably more optimization we could do. We could probably test it under higher load to make sure that our visualizations are actually functioning to the level that we hope them to. I don't know if anybody else has any comments on that.
Yeah, I can add a comment to Nabil's question. So when we set out to build this project, we actually were more interested in the engineering challenge and solving it and creating a solution that actually provides real value to the marketplace. And our project is an open source project. It wasn't built to be commercialized, or we didn't set out to like create a startup or anything like that. We're more interested in the engineering challenges within this problem domain and how we could tackle them in a way that hasn't been tackled before. Actually, when we were doing research for the existing solutions, most, if not all of the existing solutions, they have they rely on particular sets of architecture component like Firehose. And as we mentioned in our presentation, Firehose does have a lot of drawbacks when it comes to having real-time dashboard updates. So in our solution, we were able to have a more of a truer real-time experience when it comes to the dashboard updates, as opposed to existing solutions in the market. However, again, this is an open source project, and we were more focused on the engineering side of the problem domain, as opposed to commercializing it or selling a service, if that makes sense. Hopefully that answers your question.
Thank you, Med. So we have an interesting question from Vincent in the webinar chat, and he asks, what are the new technologies or skills you had to acquire to successfully complete this project? Or did you work with the ones you already knew and were familiar with? This is a great question. I think that we all were exposed to a lot of really interesting technologies and skills in this project. None of us had ever worked with just from the basic things, like none of us had ever worked with a columnar database before. We had experience with SQL and writing SQL queries with Postgres, but working with columnar databases is different. And there was a whole bunch of other things, like none of us had a lot of experience with AWS specifically. So like Jason and Med in particular they learned a lot. They did a lot of learning really quickly about AWS to do this project. I don't know if anybody has any comments on that. Okay, and we have a question from Rodney, who is our project mentor. So shout out to Rodney Matambo. He's great. And Rodney asks, now that you're at the end of Capstone, how is the journey in retrospect? Does anybody want to take this question?
Yeah, sure, I'll take that one, Michael. So it was long and tough, but definitely worth it, you know? It was cool to put this like huge challenge in front of us when we decided what we wanted to do, and it took like a lot of like determination to just kind of like chip away at it. And it was cool to see kind of like how the project changed, like what Jason was talking about and what Med was talking about, and how the project kind of like transformed. We really saw we really made those decisions. Like we said, our user is going to suffer if he has to maintain his HTTPS certificate and everything. So it was really cool to kind of like be a part of all of those conversations and see the project transform.
It was really quite the journey in retrospect. It's amazing how far we've all come.
Yeah, totally. It was an incredible experience. We learned a lot. We actually learned many technologies from the beginning of Capstone up to now, up to the implementation of the Capstone projects, like from WebSockets, SS service and events, how to deal with real-time data, how to track real-time data, and managing, working with common databases like Michael mentioned. It definitely was a worthwhile experience.
So Nabil has another question, which I think is interesting, which is, are you aware of any services in development or new tech that could replace Canopy in the short term? This is an interesting question because we designed our project specifically for the AWS CloudFront CDN, kind of for this reason, where there are actually a lot of existing monitoring solutions provided by like the CDN provider itself, but AWS doesn't provide the same like robust monitoring services natively for CloudFront real-time logs. And there's a lot of third-party SaaS solutions available that we've mentioned, like Datadog and New Relic, but there aren't as many of these robust open source automated deployment solutions for CloudFront specifically. So like Med was saying, we're mostly focusing on the engineering challenges of this product. It's possible that a competitor could come along and knock us out, so to say. But also it seems like a space that has some real need for CloudFront specifically. Any further questions? I hope I didn't miss any. Sorry if I missed anybody's questions. Thank you all again. Oh, okay. Vincent has another one. And I think we can go until 5, by the way. We can go until the end of the hour. And Vincent asks, what would you have done differently now that you've gone through all of it? Honestly, for me, I'm not sure I would have done anything so differently. I think the Capstone staff, first of all, do a really great job organizing this program. Obviously, this project is only possible because we are part of the Launch School Capstone program, and all of the instructors and organizers are phenomenal. And I think we all learned a lot along the way. So if we were going to go back in time and do it again, we would have to learn all these things all over again. So I can't think of anything I would have done differently, although because Jason and Med spent so much time wrestling with AWS docs, maybe they would go back in time and not have to wrestle with those AWS docs.
Well, at least for me, I'm pretty cool with it. I got to develop some of my DevOps skills for this particular area, so in particular with the cloud development kit.
And the SDK as well, right? The software development kit.
Yes, that one as well.
Hopefully that answers your question, Vincent.
Okay, well, I think I think maybe we can call it there. Yeah. So thank you all for attending the presentation, and thank you all for the great questions. Really, there's a lot more questions than I thought there were going to be, and they're all really good questions. Thank you guys so much. And hope you have a great weekend and rest of your day.
Thank you.